when you define some pre-variety, so it's some kind of, recall this definition. XOX, you call it a pre-variety. Of course, over a field, you have to fix some field K, algebraically closed, assume, for simply for is independent of one can define without algebraically closed condition. But let's assume everything what we are doing now is over algebraically closed field. So then, when you define this, then what you do is X is a topological space and OX is a sheaf of K algebra. So what is this? This X is a topological space and OX is a sheaf of K algebra. But not any sheaf of K algebra, it is some kind of subsheaf of K valued function. Sheaf of, so this Fx is nothing but sheaf of functions which takes values in K, right? A sheaf of sets. So every open set fxu is something like fxu is nothing but all the functions u to k which satisfy some sheaf property. This is what. Now among them you take this. This may be any arbitrary function. F can be. It may not be any regular function, but you take the K algebra. So OX is, so this is how you define a pre-variety. And then okay, so this is what was called K space. So this is not a pre-variety. It's, you still need some more conditions. So it's called some K space or something, right? K space. And then you say that it is a K variety, XOX is a K variety if you have a open cover, say X is union of UIs, open cover, say find a open cover. Huh? No, X is any topological space. X is union of UI, open cover, such that when you rest this XOX, whenever you have some sheaf, you can restrict to UI. Or in other words, that whenever you have a sheaf UI is open subset. So you can talk about UI and OX restricted to UI. Then this is isomorphic to some affine variety. So by the way, if you have a affine variety, the ring of the K valued functions, the regular functions that form a K algebras, right? Sheaf of K algebra. So, right. So what does it mean? That means for if you take, so that means if you have a affine variety, so so suppose X is a affine variety, say X is AN. Then if you take this sheaf of regular functions, then this is a K algebra, right? This is a sheaf of K algebras. And they are taking values in K. So in particular, they are pre-varieties. So affine varieties are example of pre-varieties. Okay. So now pre-variety, you say that locally it looks like a affine variety. That is the definition. And then you say that variety means that if the diagonal is closed, and so those things. So but the point is that this pair actually What I want to emphasize that if you start with the affine variety, say x is a n, then you have the natural sheaf x ox. This sheaf of regular function. This is very important object because everything is modeled on this. And we will see that not just this affine varieties, you have the more general objects are quasi-affine varieties. So what is called quasi-affine means the open subset of affine varieties. So quasi-affine means open subset of affines. And one can define regular functions. Since regular functions, one can define for quasi-affine varieties. Seems exactly same way that that it is like f by g. At a point, it is regular if it looks like f by g, where f and g are polynomial. Exactly same definition for quasi-affine varieties. Okay. So that also, so OX also you can talk about sheaf of OX, the sheaf of regular functions. That's OX algebra. But now the point is that that if you have something like XOX, even in the if you have two affine varieties, say X and Y, when you define morphism, you say phi is a morphism from X to Y. How did you define? If for every open U is a morphism, assume XY are quasi-affine. XY are quasi-affine. Does not matter. Open, if for every open U in Y and every F in OY of U, regular function, this F composition phi, which is a map from phi inverse of U to K, is regular. Is regular. So that means OX of phi inverse U. This was the definition, right? You say it is a morphism. Is a morphism if for every U, so many data. See, that's the problem with the. So this is like a. It's not just a map, continuous. So it's a morphism if first of all this is a continuous map. That I forgot to say. Phi is continuous plus not only just a continuous map. So when you define morphism between topology or space, it was just a continuous map. But morphism between affine varieties is not just a continuous map. It is more. It's more means is a lot. Like for every U in Y and every regular functions on Y, the composition is regular, has to be regular. So there are so many datas, right? So morphism between affine varieties is no joke. Or morphism between quasi-affine varieties. So that is why it is so special. The maps of affine varieties, just a continuous map, if you just give, that's not going to give you a morphism of algebraic variety. So morphisms are very special. Okay.
This Y also are quasi-affine.
Yes, assume quasi-affine.
Y.
Yes, X, Y both are quasi.
Sorry, this open set.
Huh?
This U.
Yes, if U is quasi open subset of Y and Y is open subset in some AN, so that means U is also quasi-affine. But the point is that for every U in Y, see, so you understand for every so many for every U in Y and for every F in OY of U. So the amount of data you can imagine is enormous. Now the point is that can you reduce it? Can you reduce? So checking a function is a map between affine varieties, then it will be very difficult to work with, right? To check so much every time you have to check. So there must be some nice way to work, right? So this is the point that okay. So before that, we already saw I already gave a hint that morphism between affine varieties is same as morphism between K algebras, right? I already told you, but we can generalize that. So we can replace one affine by quasi-affine, right? So that is the theorem. So I will just, but before that, I need to define some more things. I should say that how this sheaf of functions looks like. This is sheaf of regular functions. Okay, so before that, let me do this some easy things. So these are some easy lemmas. So first see lemma. Okay, before stating the lemma, let me state the theorem first, and then we'll see that whether we can prove it in today's class or not. We should be able to. Let me say the theorem. A proposition. So proposition. So when I write quasi-affine K, means this is category of quasi-affine varieties. And when I write affine K, this means it's a category of affine varieties. Right. And you know that one is contained, and this is a full subcategory. A morphism between, because the definition is via regular functions. So this is a full subcategory called affine varieties. K affine varieties is a full subcategory of quasi-affine variety. But the point is that if you take some object in X in say X is in Q affine quasi-affine and Y is in affine, then you can talk about morphism between X and Y. And since X is quasi-affine, Y is affine. So Y is affine means Y is also quasi-affine. So you get a morphism in this category, right? And since these are affine varieties or quasi-affine varieties, I have regular functions. They are K algebras, and you know it's the opposite functor, that algebra of so you have this OY and OX. But you see, OY is regular functions on Y and OX is regular function on X. So obviously, if I have a map from X to Y, that will always give a map from Y to OX. That's not a problem, because phi inverse of Y is X. Right? You can just combo. But just giving a OY to OX does not mean guarantees a map from X to Y. Because regular functions are, for every open set you have to prove. This X to Y, here Y is an open set, you take the big open set. For that you do. You understand? So now the point is that this is a bijection. Understand? This is a big result, right? You're reducing everything to only to the global functions. You don't have to look at for every open set. When you define morphism from X to Y, it is for every open set you have to check. But this proposition says that no, you just have to see at the global level. And in particular, when X and Y are affine, you have this OY and OX, these are finitely generated K algebras. So then you see that this is, but when YX is quasi-affine. We don't know whether it is finitely generated. So I'll just question. X is quasi-affine. OX, is it finitely generated? Is it reduced? Because we saw that in the case of affine, these are reduced finitely generated because Y is irreducible. So it has no nilpotent, so some quotient kx1, x2, xn modulo some prime ideal. So that's a finitely generated algebra, and which is reduced because it has no nilpotent, right? Nilpotent elements are intersection of all prime ideals. Right here, you don't have any prime ideal which contain 0 itself is a p is a prime ideal, so that will correspond to the 0 ideal. So this is a but you see the implication is huge in the sense that you really don't have to. So that's what I said in the beginning. I always try to say that morphisms are more important than the underlying varieties. You see, this is an example. The morphism between a variety is determined by the what is happening at the global level. Whether you have a morphism of the OI to OX, right? So functions are more important. Regular functions. Right? Because to check a map from X to Y, you have to check for every open set. But that's not a healthy way to check. But this is much more easier. You just have to check whether you have a K. Every K algebra map will induce a map from X to Y. When we see the proof, we'll see how it is. But this is a first, at least some, what do you say, that it shows how the subject grows. The functions, the regular functions are more important than the underlying. So one should be always careful because a map between affine varieties is just not just any. It's not an innocent map. It's not an innocent thing. It involves a lot of things. Okay. So before. So this, I'll say this is the dawn of the subject. This will show you, this will be reflected everywhere. Whenever you define something, any algebraic variety, you don't think any, like topological space or metric space, the X was important, right? By where you are. Here you see the X is not very important. The important thing is the functions on X. If you know the functions of A, if you understand that, then you understand X. It's more like a function analysis approach. That's how you study. So in function analysis, also you study your whatever analysis you do on some space. You study through its functions. It's more like function analysis. Okay. So it's like okay. Anyway, let me not say anything more, but let me state some easy results first, and then we'll prove this. Yeah. So recall, suppose you have a affine variety, say, and okay, let's assume quasi-affine. And if you have a regular function, say f y to k, so k I can always identify with a1k, okay? I can give a topology because a1k is a topological space, it's a affine space. So this is regular, f is a regular function. Implies f is continuous. with respect to Zeiss topology. So this is one. This is not easy, difficult. And then if you have two regular functions, if f g from y to k, if they are in your OY, if they are two regular functions, and U is some open subset here. Sorry. Such that f restricted to U equal to G restricted to U, then f equal to G on Y. So this is if you have two regular functions, if they are in they are same on an open subset, then they are same on the whole Y. Proof is easy. So regular functions are continuous functions. What you have to say that if I take some closed subset in A1, the inverse image is closed. But what are the closed subsets in A1? There is disjoint union of some finite sets. So it's enough to do it for the finite point. So what? Yes. So it is enough to prove that you have to this is closed, right? But again, f is a regular function. So that means if you have a right, so that means if you take some point P here in F inverse A, you have to say that F inverse A intersection, there is some how do I say? Okay, so suppose this is so f of P equal to A, right? But f is a regular function. So what is the definition of regular function? Locally, so there exists an open subset UP such that f restricted to U is G by H. Right? So this is on. So that means this is same as saying f on U or f equal to G by H on U, and H of P is not 0, right? Because H is regular, it is HP is not 0. So then you consider G minus f of H. G minus f of H. So now this G minus f of H, yeah, so you find a set where it is 0, but that's a closed condition. So locally every point you have a closed subset. So that means this function is continuous, right? Right? For every P, I have a closed subset. So
this set is closed.
Yeah, so this is a closed condition.
So how do you know that the inverse image of f at the point A is same as the inverse set of this P? How do you know the P image of f at that point A is same as the places where the string value?
See, if at a point so I want to prove that what F inverse of A is closed, right? All right. So that means if I take a so how do you prove this? Yeah. So you take the regular function f on u, and then F inverse of A is nothing but the zero set of G minus Fh, right?
G and H at the point.
Sorry, not Fh. Sorry, F. Why I am writing F? G by A, F is equal to A, so it is A. Sorry, AH. Yeah.
G also, then with the G.
G is a G is a polynomial function. G is a polynomial. H is a polynomial. They are all continuous function, right? So G minus AH is a continuous function. Now you consider zero set of, right? So F inverse A is closed then, right? For every point P, right? Okay. So now second condition, if F and G are open, sorry, F and G are on U, if it is open, then so you have an open subset U in Y, so the F restricted to U is G restricted to U, then I want to prove the F equal to G. But you see again that F equal to G, right? So consider F minus G. Now you consider as a zero set of F minus G. Now this is a continuous function. So it is F minus G inverse of 0. Zero set of F minus. So this is a closed subset. Right. So this is so this is a closed subset of Y. And U is an open subset of Y contained in zero set of F minus G. Right? But yeah, so quasi affine. So that will say that Z of F minus G equal to Y. But if Z of F minus G equal to Y means Y F equal to G on Y. Right? Okay.
So in the first part that continuous, we proved that this continuous within a neighborhood.
Yeah, but that's how you prove continuity, right? When you don't have a function globally, see, when you have a regular function, you don't have a function globally. So locally, you prove that there you have it's a closed set. That's how you. The function f itself is not defined over the. You say it's a regular function. That does not mean it's a global function. So defined only on locally. So locally, you prove that it's a closed subset. So the where it is same. So for you take the union.